Several 611 students have requested a lecture that provides additional background and tips for Lab 2, so this week's lecture will be just that. Before we begin, we will write and test a RISC-V program that we can use as we incrementally design and test our CPU hardware. Lab 2 requires that you write a binary to decimal converter. So we'll write a variation on that. That's a bit different in that we'll write one that converts a 9-bit binary value to a 3-digit decimal value, as opposed to the 18-bit binary to 6-digit decimal converter that's required in Lab 2. The difference is that obviously we only need to extract 3 decimal digits from the binary input value instead of 6 or 8, depending on how you write the code for Lab 2. And we'll use a fixed point data type that uses 16 fractional bits instead of 32 fractional bits, as we call for in Lab 2. This is just to make the program a bit different, but it shouldn't be too hard to adapt this program to the one you need for Lab 2. Okay, so let's go over here to RARS. Now the first step in your RARS program is to read the input value, so we'll go ahead and add a CSRRW instruction, and we'll read the state of the switches into register 1, IO register 0, which is the switches, and then X0, which is a placeholder, which would normally be used as our output register, but we're doing an input operation. Now in this case, we're going to comment this out temporarily for the purpose of testing in RARS. We'll replace it temporarily with a load immediate instruction, where we'll load a fixed value into register 1 that we can use for testing. So we'll pretend like the switches are set up with a value of 768, which of course we can change whenever we want. And then before we put this on our CPU, we'll uncomment the CSRRW instruction and comment out the LI instruction. Okay, so the next step is to basically initialize a series of registers. So the first register we'll initialize is the next one in sequence here, register 2, which will be our output register. This is the one that will be sent out to the hex displays, will contain the value converted to base 10. So we'll initialize that to 0. Next we'll initialize X3 to be the 0.1 value in fixed point. So we're using 16 fractional bits. So to get 0.1, we multiply 0.1 by 2 to the 16th power, or 0.1 times 65,536. And so rounded, that would be, instead of 65,536, we're taking a tenth of that, which is 6,554. So that's our 0.1. Basically, we'll treat it like a constant. And then we also need, of course, 10, constant of 10, which we'll put in the next register, which is register 4. And then because we're using a 16-bit fixed point type, we're going to need a way to mask off the lower and upper 16 bits of a register. So for that, we'll set up some bit masks here in register 5. We'll put in a bit mask for the lower 16 bits in register 5, and a bit mask for the upper 16 bits in register 6. Now I'd like to point out that both of these instructions are putting 16 bits into a register, whereas the RISC instruction set architecture only supports 12-bit immediates. So these instructions are, as well as the first of the load immediate here with the 6,554, all three of these load immediate instructions rather, are requiring more than 12 bits. So they're going to be treated like pseudo instructions. So be aware of that. When you execute this program on your CPU, you're executing machine instructions, not assembly instructions. So these instructions will have been expanded, but we'll look at that when we assemble the program. Okay, so at this point we can go ahead and start the conversion process. So we'll multiply the input register X1 by 0.1, which is in X3, and we'll put the result into X7. Okay, and so this should give us, it should take us from 768, which is the input, to 76.8, 76 being in the upper 16 bits, 0.8 being in the lower 16 bits. So the first thing we need to do is isolate the upper 16 bits and basically use that to replace X1, because we're going to be whittling down the 768 one digit at a time. So I'm going to do a shift right logical arithmetic. I'll take register 7 and shift it 16 bits to the right. I'll put the result back into X1, so that will replace the 768 by 76. So back in register 7, we still have the full 76.8. We need to knock out the integral part, the 76. So for that, we'll go ahead and do apply our bit mask. So I'll do an AND. So I'll AND X7 with, let's see, we went the fractional bits, we went the lower 16 bits, so that would be X5. So this leaves us with 0.8. And then we can simply multiply the 0.8 by 10, which is X7, we multiply that by 10, which is an X4. So this would be 0.8 multiplied by 10, should give us 8. Again, the 8 is now back in the upper 16 bits. So we need to do another bit mask there. So we can isolate the upper 16 bits with the upper 16-bit bit mask, which is in X6, register 6. Now you might be thinking, wait a second. Why do you have to mask off the fractional bits? Because if you had 0.8 and you multiplied it by 10, you should get 8.0 with no fractional part, which is true, except remember that the 0.1 wasn't exactly 0.1, because when we divided 65,536 by 10, we had to round. We had to round up to 6,554. So the 0.1 wasn't exactly 0.1. So when we get the 0.8, we might have not got exactly. When we expected 0.8, we might not be exactly at 0.8. There might have been some round off error. So to be safe, I'm going to go ahead and mask off any fractional bits that might have been left over from the 0.8 times 10. Okay, so now we have our rightmost digit of 768, which is 8. It should be by itself now in the upper 16 bits of register 7, which is bits 19 down to 16. Now, what do we do now? We need to be able to put it into the correct position. I think the easiest way to do this actually is to take each digit and put it in the leftmost output digit, and then before we do that, each time we can shift everything down. So basically, the 8 will go into the first digit, and then the next time we'll shift that 8 down to the second digit, and the third time we'll shift down to the third digit, right? So what I mean by that is we'll do a shift right arithmetic. We'll take X2, which is our output. Now, right now, X2 is 0. So shifting 0 by any amount seems redundant, but I'm going to do that just so I can copy and paste this code for the 3 iterations of this program. So I'm going to shift X2 by 4 bits. That's one hex digit, or one base 10 digit, one decimal digit. Shift that to the right by 4. So then I'm going to shift X7 to the right. So currently it's in bits 19 down to 16. I want to get it into the leftmost digit of a 3-digit decimal number, which will be bits 11 down to 8, because your 3 digits are 11 down to 8, and then 7 down to 4, and then 3 down to 0. So if I want to go from 16 down to 8, I'm going to have to shift that by 8 bits, and then I will use an OR instruction to just go ahead and merge that digit in, just to drop the new digit. Now again, the digit in this case is 8, so I'm dropping the 8 into the leftmost of 3 decimal digits. But when I copy and paste this code 2 more times, after the whole program is done, that 8 will have worked its way down to the rightmost digit, which is that's where it should be, because it's 768. So great. So I'm going to take this and paste, and then when I'm done, the only thing left to do is to do a CSRRW. And let's see, which I/O register is the hexes? It's 2. Okay, so in this case, the first argument is placeholder x0. The second argument is I/O register 2, which is hex displays, and then we're writing the value that's in x2. And that's it. We are done. So I will save that, and I will assemble it, and now it's time to test it. So let's just go ahead and step through here. So I'm going to leave the general purpose registers here in hex. So let's see. So we're going to put 300. Okay, so we've got 300 in register 1. That's our input. Over here in settings, I'm going to turn off values displayed in hex just to verify, yes, that 768 is in register 1. Okay, great. And then after that, it's basically just some initialization. So let's see, register 3 was going to get the 0.1, which was 6,554, which is correct. Register 5 was going to get 10, correct. And then registers 5 and 6 were going to be our bit masks. So for that, I need to go back to hex. Very good. So 5 is our bit mask for the lower 16 bits, 6 is our bit mask for the upper 16 bits, and then finally register 7 is the result of the multiply. Now, when you take 768 and you multiply it by 0.1 in fixed point, it's not, you can't directly just look at the result and validate that it's true. You'd have to do the math in integer form. But I'm going to go ahead and just skip forward a bit because we're expecting that that register 1 should become 76 after the shift, right? So let's see if that happens. So let's go back over here to decimal, and then we can step forward, and there we go. Register 1 is 76, so we've shaved off the 8. And then the next step is we're going to put 8 should go into the upper 16 bits after we do our bit mask there. So, and again, it should be register 7. So if we go back to hexadecimal, we should see register 7. The upper 16 bits of register 7 should be 8, which it is. And notice that we do have some, as I predicted, we have some fractional bits, kind of residual fractional bits in there, which should get knocked off here after our bit masks. Very good. So there's our 8. And then we are going to shift that down to the third digit from the right. So that's where the 8 should go. There it is. Okay, 800. So it's 800, but eventually that 8 will be in the 1's position. And so now we work off to our second digit. So I'm just going to kind of blindly step through here a bit. Because I know that register 1 should become, and I'm going to have to go back to decimal. So register 1 should become 7. There it is. And if I go back to hexadecimal, I'm expecting register 7 to become a 6/8. Oh, rather, sorry, register 1 should become, or sorry, register 2, rather, sorry, register 2 is our output, and there it is, 6/8, you see, so we've got the 6/8 from 768, and register 1, register 1 is now 0, which of course makes sense because the 7 is now gone, and so we've shaved off the last digit there, and then eventually register 2 should become 768, and there it is. There's our 768, and then we're done. So that is the program. It seems to be working. So I'm going to go ahead and dump this program out to hexadecimal text, which will allow me to read this program in my CPU. I'll call it program.rom, and I'm going to put it into the lab RAU. Program.rom. I should put it in the RTL directory because that's where it'll be read. Yeah, I'm going to put it in the RTL directory actually. So my program.rom is going to be in the RTL directory. It'll be in the same directory. Actually, you know what? Come to think of it, I'm going to actually put it in the root directory of lab RAU. Yeah, because the HDL is in the RTL directory, but when I'm actually simulating it, I'll probably be in the root directory. So I'm going to put it there. I can always move it later if I need to. So I'll hit save there, and it says program ROM already exists. I'll say yes on that. And now it's time to move on to designing the hardware. Okay, so we'll start our hardware design from the top down. So we're here in the lab RU folder. Let's start with simtop.sv. RTL. Now let's start with simtop.sv. Okay, so that's a little hard to read. View, preferences, colors, presets. Let's do black on white. There we go. It's a bit easier to read. Okay, so our simtop is the top level design, and right now there's nothing in there, so we need to instantiate our CPU. So we'll call the module CPU. I'll name the instance my CPU, and it'll have an input called clock, which will wire up to clock 50, and then it will have an input called reset that will wire up to key 3, and it will have an input for the switches, so we'll call this switch in, and this will be wired up to SW, which is an 18-bit value. Now we probably should make this 32-bit, a 32-bit input. So I'll go ahead and just add, let's see, 32 minus 18 is 14. So we'll go ahead and put in 14 zeros along with the 18 switches there. And then we'll have hex out, which now the hex out is, it can't connect directly to the hexes because it's going to have to go through the 7-segment decoders. So I'll probably just have an intermediate internal signal here called hex out. And I believe that's all we need for that. So I'll go ahead and declare hex out, and that looks good. That looks good. Okay, so let's go ahead and save that, and now we'll edit cpu.sv. And so actually, let's do this. Let's do v split simtop. Okay. So I want to copy this, and I want to paste it here so I can get these ports correct. So we've got input logic clock and input logic reset and input logic 31 down to 0 switch in, and output logic rather, output logic 31 down to 0 hex out. And then end module. Okay. So we were hoping that, let's see, set tab stop to 4, set soft tab stop to 4. Go ahead and save that. Close this guy. Okay, so now the intent was for you to be able to design this directly from the slides. So you can see that you know, we can start with fetch to code. So we have you know, instruction memory PC PC incrementer here. That code is actually shown down here. So we'll go ahead and just basically start with this. We've already dumped the hex file here. So I'm going to go ahead and we'll copy that, paste that, and copy this, and paste that. Okay. All right. So this will declare our instruction memory. It is a 4K deep by 32 wide memory. We will initialize it. Notice in the slides I forgot I have an initial and I have an end. I don't have the begin. So either you have to add a begin or delete the end. I'll go ahead and just I'll just delete the end actually. The other issue here is make sure that you replace these smart quotes with regular quotes. And the other, finally, get rid of the 0.1023. This actually causes an issue with Verilator, which is was posted on the forum. I apologize for putting those numbers in. Okay, so now let's see. We have 2 instruction mems here. Oh, that's right. Somehow I pasted that twice. I meant to copy and then paste. There we go. Okay, so now we have always FF pos edge clock. Clock signal's correct. This always FF does not have a begin or end because the if statement here is counts just as one statement. So I'll go ahead and leave that the way it is. So if we have a reset, I'll set the instruction output to be the no-op, which is all zeros. Be sure to replace the smart apostrophe with a regular apostrophe. This comment here, by the way, this add I x0x00 is actually how this no-op will be decoded inside your CPU. And the reason I note this is because in your simulation, you may see that this no-op actually writes to register 0, which it's you know, that's what it says to do, but writing to register 0 doesn't have any effect on your CPU because register 0 will always return the value of 0 when you read it. So even if it's written internally, it's whenever you read. So writing to register 0 has no effect, essentially. So let's see, replace this smart quote. So in addition to sending out a no-op on a reset, I'll also reset the program counter to 0. And otherwise, the instruction EX will be the instruction mem at PC fetch, and the PC fetch will be incremented, and I need to replace that smart apostrophe. Very good, and end. Okay, so now I'm loading a file here called hexcode.txt. I'm going to replace this with program.rom, which is what I called it when I exported it, and we should be good to go now. So I'll go ahead and just compile this. Now, this is the part you have to be a little bit careful about. I'm going to go up to the, so I'm actually in the top level of the project folder. So I'm going to do a vlog on the CPU and SimTop, but those are both in RTL. So I'm going to do a vlog RTL, and actually, you know what? I'm just going to say star.sv. I'm just going to compile everything. Okay. So I did get some errors here. Instruction EX and PC fetch. I forgot to declare those, so that's not a problem. I'll go ahead and do that right here. I'll declare logic 31 down to 0, instruction underscore EX, and logic. Let's see, PC fetch. This is it's addressing a 4096 4K RAM, so obviously it's the address number of address bits here would be the log base 2 of 4096, which is 12, so that would be 11 down to 0 for the PC fetch. All right, so I've got my instruction EX PC fetch. Go ahead and save that. We'll try another compile. Okay, so no errors, but just going to scroll up here to make sure. Yep, no errors. Very good. Okay. So now I should be able to go ahead and simulate this, except I need a test bench, obviously. So let's see. For my test bench, I should create a test bench that wraps around SimTop, probably, right? Because SimTop wraps around my CPU. So I'll go ahead and create a tb.sv, and so module test. Let's see. Let's call it. Actually, yeah, I'll just call it tb, and module. No inputs or outputs because it's a test bench. And so this will instantiate a SimTop, myTop, and then I need to bring in everything here. So let's see, let's do a split and open up simtop.sv. And so if I come down to, actually go up to SimTop, I can go ahead and copy all of this stuff. Let's see, I'll put that in there, and I'll go ahead and, let's see, modify this a bit. So let's see, can I do a, let's see, a search for input with yeah, and then, well, actually, let's see, space star. Ah, very good. And replace that with a dot globally. Very good. Oh, that didn't include the, yeah, that's okay. Deal with that later. And then I'll go ahead and, let's see, I'll replace output with 0 or 1 more occurrences of space with a, dot. Okay, yeah, that's good. Okay, no problem. Okay, good. So I'll put the clock in there. I won't connect anything to those guys. And over here, let's see, LEDG, not connecting that. LEDR, not connecting that to anything. Let's see, key. I'll put, I'll have a key, my own key, switch, I'll have my own switch, and, yep, and then I'll have hex 0, and just 1, 2, 3, 4, 5, 6, 7, just delete these guys, and, let's see, 1, 2, 3, 4, 5, 6, 7, and for now I'll just leave these unconnected just for the moment. Eventually I'll want to connect those, but I'll go ahead and leave them unconnected. So really all I need to worry about here is clock and the switch. Or the key rather, and the switch. Okay, so then I'll declare some stuff for that. So logic clock, logic 1700 switch, and logic 3 down to 0 key, and then always begin, and I'll say clock equals 0, we'll wait for 5, clock equals 1, we'll wait for 5, and initial begin end, and we'll say key equals 0001, oh no, sorry, it's key 3, right? Yeah, there we go, 1000, we'll wait for 10, and then we'll set key to be 0. Okay, so that'll drive our clock and our reset, and we need a simulated switch, so I'll just assign switch to be 18.768. Now, I forgot to change that load immediate inside my code for loading the switch value, so I'll have to remember to do that, but I'll just leave this the way it is for now. Okay, so back down to here, let's go ahead and compile everything. We did have an error somewhere in the test bench, line 49. We have some, that should do it. All right, let's try that compile again. Looks like it worked. Okay, very good. So I should be able to do vlog tb. Oh, sorry, vsim tb. Sorry. Okay, so this will open up model sim. Oh, looks good. Loaded it up. I'll go ahead over, I'm going to drill straight down to my CPU, and I'm just going to drag all that stuff over. And I'll hit this little mountain button to take away from the prefixes there, take the prefixes off. Go ahead and run that. Okay, so you can see that clock and reset are good. And the reason I wanted to simulate this at this point was to just verify that my instructions are coming out. So if I switch, and of course that my program counter is running, so you want to make sure, let's change the radix here to decimal, or actually probably, well, it should be unsigned technically. And then the instruction out will make that a hexadecimal. So we should be seeing the instructions. So we need to be able to cross-reference these guys with what's in. Let's see. So we should be seeing 3 and 5 zeros, 9, 3. That's the first add I instruction. Are we seeing that? Yep. Okay, then it's a bunch of zeros and 1, 1, 3. Let's see, are we seeing that? Bunch of zeros and 1, 1, 3. Yep, there we go. So, and then of course, bunch of zeros, 2, 1, B7. That's the next one. A bunch of zeros, 2, 1, B7. So yeah, it looks good. Looks good. We're good to go. Good. All right. So let's go back to our editor. Okay. So let's see. So we can close the test bench. We can close the SimTop. Let's go back over to our CPU. Okay. So now inside the CPU, we are done with the fetch stage. So now we need to add our register file. So let's open up the reg file that we provided you, and let's go ahead and just yank that and yank and put that. So we'll go ahead and stick in our register file. So I'll call it my reg file, and we'll do our trick again. So okay, so now we have our register file. So let's save that, and let's open up on the top, we'll open up the CPU.sv. So this way, as we add internal signals, we can add their declarations up here. Okay, so the first thing we need for our register file is a write enable. So actually, let's just follow what we've got on here first. So, so obviously clock is our clock. Now read address 1 is the instruction EX 19 down to 15. And read address 2 is instruction EX 24 down to 20. And the write address is going to be called regdest write back. Regdest write back. And that one we need to declare. Oops. Sorry. Regdest write back. Okay, so we can come up here and declare that as a 4 down to 0 regdest write back. Okay, and so it looks like that pretty much completes everything on this slide. Oh, we have a register here. So we'll have to add that register too. So let's go down here and go ahead and add that register. So for that, we'll say always underscore ff at pause edge clock begin, and we'll say regdest write back is assigned to instruction EX, and according to this it is 11 down to 7. Okay, and adjust that. Okay, so now we have much of the register file wired up. Let's go ahead and skip down here and see what we have to do next. So now we have to keep working on our ExWB stage. And so for this we're going to need our ALU. So I will go ahead and let's open up the ALU that we provided you, and Yankaroo. Well, actually, yeah, that worked. We're good. And then put, and then close that. And let's go ahead and transform this into okay, so according to this, we have an ALU, we have our ALU gets the A input directly from the register file. So we will go ahead and add a wire there. Now notice I didn't label that wire here, so we'll have to come up with our own name. So I'll call it A. So we'll declare an A. Logic 31 down to 0A. And we will connect A. So A is driven by the register file and it's read by the ALU. So that takes care of that wire. Now we have the second, we have a mux here. So we will, and again, I didn't label the output of the mux, so we'll just call that B. And so we'll need to add a B there. And we will need to create a mux for that B. So we'll add always, actually I'll use an assign for this. So assign B equals, okay, and that's either going to be the second output from the reg file. So what are we going to call that? We'll say reg, I'll call it reg data 2 EX. And that will depend on the value of ALU source. So we'll say ALU source underscore EX. If that equals, well actually if it equals, yeah, we'll say if it equals 0, then it'll be reg data 2 EX. Otherwise, it will be the sign extended immediate, which would be basically just, you know, how do we sign extend the instruction? Well, first we need to know how many bits to sign extend. What would be, let's see, this is only a 12-bit immediate, so we need 20 bits of sign extending. So we will use the duplication operator here. We'll say 20, and we'll copy instruction EX bit 31, which is the sign bit, and combined with instruction EX31 down to 20. So that is our sign extended immediate. And so now, before I get too far ahead of myself here, we need to declare a few things. We need ALU source EX. So we've got that guy. So we've now declared that. We've already got B. The instruction, of course, we already have, and reg data 2 EX. So 31 down to 0, reg data 2 EX. And so we come down to the register file here and wire up reg data 2 EX. And by the way, this should actually be AEX to be consistent. So let's just change the names of those here, just so we denote that those are in our EX stage here. So EX, okay. Okay, so we've got the ALU, we've got the MUX, we've got the reg file wired there, we've got the sign extend done. The reg dest WB, I believe we have that there. Yes, we have that. Okay, so we also need a register for our hex out. So I'll go ahead and add that. So we'll add that to our registers here. Hex out is going to be whatever's coming out of the reg file, which is AEX, and that will happen only if hex write enable EX is set, and so then we will declare that as well. Okay, so now we've got the hex out, and then if we scroll up here, we need some additional signals here for the write back stage: reg write back and reg select EX, reg select write back, right? So we'll declare those. So reg write back, as well as reg write EX, and reg cell write back, and reg cell EX. And since that's controlling a 3-input MUX, then that will have to be 2 bits. Okay, and then so we can go ahead and add those to our pipeline registers. So reg cell write back equals reg cell EX. We need to change those to non-blocking. Okay, so we have those 2 registers done. Meanwhile, we have switch in. So we have switch, let's see, switch in write back equals switch in. What did we call that? Yeah, just switch in. Okay. So that register is done. Then we have this register over here. We didn't label it here, so we need to give that a name. So I'll call it LUI val write back is going to be instruction EX 31 down to 12, concatenated with another 12 binary zeros. So that register is done, and then we have RX and RWB. So RWB is REX. And we need to declare those. So we have logic 31 down to 0, LUI val write back, and as well as logic 31 down to 0, R write back, and R underscore EX. So those are both declared. We also have write data write back, I see. So write data write back, that's this guy, and reg write back, which I believe we already have reg write back. Yeah, we just need write data write back. All right, so okay, so the write enable for the register file is going to be connected to reg write back, and the write data is going to be write data write back. Okay, so we have these two guys connected. The ALU output is going to be called REX, which we believe we have declared here. We have an op, ALU op EX, which we will need to declare. That's 3 down to 0, ALU op EX. So we have that declared here and that declared there. Let's see, anything else? So ALU is fully connected now. The register file is fully connected. And so as for this mux, we can implement that right here. So we can assign write data. Actually, one word, write data underscore write back, which is the output of this mux, equals, depends on reg cell write back. And if that equals 0, then we're going to take switch in write back. Otherwise, it's going to take the second input, which is, what did we call that? LUI val write back. And actually, since we need to specify the value for that reg cell write back equals 2 apostrophe BO1, then it will be that, and then the third option is R write back. That's the fallback option. Okay, all right, so very good. So that mux is done. Anything else we need in here? Don't see anything. Okay, so we just need the control unit now. Okay, so control unit is shown here. Okay. So for the control unit, that'll just be a always comb, begin, end, and this is just an if then else. Now one thing I want to show you, it's kind of a neat trick. One of the problems is that when you're simulating this and you're looking at the signals in your waveform, you don't really, it's difficult to tell what instruction is being executed and what instruction is being written back at each moment in time. So we can actually put a little debug logic in here that would be optimized out if we synthesized it, and I found this to be kind of helpful. Save that. Okay. Okay, so you can declare a custom type. So we'll say type def enum, and we can declare an enumerated value for each one of our instructions. So for example, add sub mul set less than, and I'm going to put an underscore there because and is a reserved word in the system Verilog. And I shift left logical immediate, load up our immediate, CSRRW, and I'll have a special version here for hex versus the switches, and then add I, and let's see, what am I missing here? SRLI. Okay, we'll leave it at that for now, and we will call this instruction name, and then we will say instruction underscore name. We'll say instruction in EX stage and instruction in write back stage. And so inside of our pipeline registers, we can simply say instruction in the write back is going to be whatever was previously in the EX stage. And then down in our control unit, we can set the EX. So we can say, for instance, if instruction underscore EX bits 31 down to 25 equals 7 apostrophe H0 from the table here, and instruction EX bits 14 down to 12 equals 3 apostrophe B000, and instruction EX 6 down to 0 equals 7 apostrophe H33, then begin and end. Okay, and let's see, there we go, bring the font down. Okay, so then we can say else if, and paste this, and begin, and yeah, we can paste this a bunch of times. And then before we get started there, actually, one thing I forgot, we want to put the values, all the default values down here. So we can, that way we can only change the values that need to be, that need to differ from the default values. So I'm going to set ALU op underscore EX is going to be set to the default for that. I'll just make it an add, which is 0011, and I'll set my ALU source EX to be 0, and my reg select EX to be 110, which selects whatever comes out of the ALU, and then my reg write EX will be 1 by default because most of the instructions write, and my hex write enable to be 0 by default. Okay, so all I have to specify in this if then else are the signals that would be different from those. So in this case, in my add, none of these are going to be different. So I don't have to do anything, but I will set my instruction in EX to be add. And also I probably should put a default for that as well. So let's see, let's put instruction underscore in EX to be, I'm going to say unknown, just in case we run into an issue where none of these match. So, and I'm going to add unknown as an option here as well, up here. So, unknown. Okay. All right. So, so next is my subtract, and I think they only differ from the ALU op. So ALU op EX is going to be 4 bits of 0100, right? Yes. Okay. And the next one is multiply. I think pretty much the same thing. ALU op EX is going to be the multiply code, which is 0101. And next we have SLT, which is also, and I need to remember to fill in the instruction name as well, 1100. And finally the AND, ALU op EX equals sorry, forget the B there. And that should be 4'B 0000, right? Okay, and then, so before I forget, let's go ahead and fill in the instruction in EX for this would be a sub, and instruction in EX here is a mul, and instruction in EX is a SLT. Okay, and after SLT we have AND. Oh, and underscore. Okay. Okay. And then we're going to change. Okay, and then we're going to need to update the instruction 7. So 0. Let's see. Oh, in instruction 3. So 20. And let's see, that would be 0, 33. That's 1. 1, 0, 33. We've got 0, 0, 1, 0, 33, and 0, 1, 1, 1, 1, 33, and now we're on to our I types. Okay? Very good. So for the I types, we need to change ALU op, and so let's see, and I, and actually in this, yeah, and I, the ALU op here would be 0000, and the other difference is that the ALU source would be ALU source would be 1 in this case, actually, instead of 0. Reg select, reg write, and hex write enable would all be the same. Okay, so next we have, and I'll go ahead and update the opcode here. Would be this guy, 7 instruction, func 7 would be I don't care, and then func 3 is a 1111, and then 13. All right, 13 is, or sorry, opcode is 13. All right, cool. And then instruction in EX is going to be SLL, no, sorry, and I. And then the next one is SLL, which would be, let's see, func 7 is 0, func 3 is 001, and 33 for the opcode. ALU op EX is going to be 4 B1000, and ALU source is default, and instruction underscore in underscore EX is going to be SLL. And then for the SLLI, that would be func 7 is 0, and func 3 is 100, and opcode is 13, and this would be an ALU op EX of 1000, ALU sources 1 and instruction in EX is going to be SLLI. And then finally, load upper immediate is a don't care for func 7, as well as func 3. We're just looking at instruction EX. 6 down to 0, the opcode would be 37. And for this, the ALU op is a don't care. ALU sources a don't care. Reg select is 0, 1, and reg write is a 1, and or default rather, and hex write enable is default. Okay. Okay, and then let's see. All right. Okay, and then we're on our last two that are listed in the table, CSRRW. So this will be if the instruction 31 down to 20 is O2, this would be the hex, so IO register 2. So this would be, if that's 2, func 3 is a 1, and the opcode is 7.3, in which case we have don't cares except for reg write. EX is going to be 0, and hex write enable is going to be a 1. Instruction in EX is going to be CSRRW hex. And then for the other CSRRW for the switches, we're looking at the IO register to be 0, which is an instruction 31 out of 20. The func 3 is 1, and the opcode is going to be 7.3. And so for this, reg write is actually 1. And reg select is going to be 2B00. Okay, and instruction in EX is going to be CSRRW switch. Okay, now, so we finished all the instructions that are listed here on the slide. We need to add 2 more, though, for the test program. We need to add the shift right arithmetic immediate and the add I. So for that, let's see, I'm just going to add an end here. So for the add I, I'm going to add that one right after the add. Let's see, so where's our add? Add is here. So I'm going to go ahead and insert that right here. So for the add I instruction, obviously 31 out of 25 is a don't care. This is covered by the immediate field. So with an add I, the func 3 is looks like 0, 0, 0, and the opcode is looking 1, 3. Okay, so that gives us our add I, and then the shift right logical arithmetic, I'll add that one down here with the shift logical left logical arithmetic. So yank that, paste that there, and I suspect these are pretty close, right? So the opcode for that would be 1001, and the func, let's see, the func3 is 101, and the opcode rather is 13. Okay, very good. And that should do it. Let's save that, come down here. Let's try a compile. And we got a lock file. Okay, so let's go ahead and delete the lock file. And let's try again. Okay, so we got some errors here. Okay, line 40. So SW in write back. I guess we didn't declare that, right? Yeah. Okay. We can add that. Logic. So SW in write back. All right. So then we had line 47. Something going on there. Probably mismatched parentheses. No? The bracket, rather, the right bracket. Okay. All right. Let's see, line 82. Hex write enable. Oh, I probably named that hex write enable EX, correct? Yes. Forgot the B. Line 118. Okay. Okay, so it looks like we compiled, so now it's time to test it out. If we go back to Model Sim, we can reload, go back into my CPU. I'm going to take out all these signals and put in all the new signals. Okay. Okay, so when testing at your CPU, the best place to start is with your register file. So if we drill down into the CPU over here and we click the register file and then go into the memory, after we add that, we need to re-simulate to get the values. First of all, let's switch that to hex. Okay. So what we're expecting to happen is the same thing that happened in our RAR simulation. We should see register 1 getting written right off the jump, and that's not happening. So there's an issue there. So to debug that, we need to take a look at what's going into the register file. Also, by the way, if you notice that the instruction in EX, instruction write back, indicates what's being executed, we can see that the add I instruction is being executed there and is being written back there. When it is being written back, we should be seeing the reg data should be getting set to 768. And if we find reg data, reg write, there's reg data 2. Oh, sorry, write data rather. Write data. There it is. It's an unknown, and so it shouldn't be an unknown because we should be seeing R write back being set, which we do not. Okay, and that should be getting set because of REX in the previous cycle. So we step back to the previous cycle, we should see REX. We don't see that. Why not? Well, that should be because we should be seeing that because A and BEX should be set. And A is set, but B is not. So that's probably why. Oh, and that's probably because we forgot to implement that mux there. So actually we did implement that mux. That was the ALU source mux. Let's check ALU source EX. And that is a 0, and of course that should be a 1. So the problem is in the add I instruction, which happens right here, we forgot to set ALU source EX to 1. And so now ALU source EX is 1. We can see that A is set, but BEX still isn't set. So if we go over here, we can check BEX is, oh, it's never set. Okay. So that would explain it. We forgot to drive that signal. That signal is supposed to be coming out of a mux that decides between the output of the reg file and the sign extended immediate. Now, I thought we sign extended the immediate. I see the problem. I see. So this should have been BEX. There we go. And BEX is now set. Very good. Set that to, let's view that as unsigned. There's the 768. So now, if we go back to the register file, we can see that register 1 gets set properly. Register 2 gets set to 0. Register 3 gets set to, that is the 0.1. Unsigned, that's the 6554. Register 4 gets set to 10, and then register 5 gets set to FFFF. Register 6 gets set correctly, and then register 7 should eventually get the value of 8. And register 1 should get 7.6, and eventually 7, and then eventually 0. Meanwhile, register 2 should get 8, 6.8, and 7.6.8. So, looks like the program is working properly. Now, let's go back to RARS and change that code such that we put back the CSRRW instruction. We'll save that, and we have to assemble it, and then we can dump the memory again to hexadecimal format, dump to file, 611, and program ROM. Yes, okay. Go back here and restart the program. And if we scroll up to instruction EX and look at the hex, we can see that the first value has a 10F3 in it, and 10F3 is in fact the correct lower 16 bits of the first instruction, so that's good. And we should be able to verify that register 1 still gets the proper value. And it does, 768. And then finally, if we look at hex out by the end, so there's the hex write enable. Now if we run this long enough, we should see hex write enable get asserted there, and we should see the hex out get set here to 768. So the program is working. So that's good. We can also, by the way, just for completeness, we can go back up here to our test bench, and we can change the switch value to have, say, 9999, and we can recompile, and we can restart and run it long enough to get a cursor, and we should see the 999 there. So very good. So the CPU seems to be working. Obviously, we haven't implemented all the instructions in your Lab 2. You will need to complete the control unit and implement the rest of the instructions, and your converter program will be slightly different. But hopefully this gave you a way to get started or a way to get unstuck if you're stuck. And if you have any other questions, feel free to contact us. Thank you.